Thank you for coming along this evening. So I'm going to give a brief talk about signals, events, signals and recommendations. And I'll start off by jumping straight to a practical example of how signals and recommendations can make a difference. So this here is a screenshot of a search results page for someone searching for a video game, Call of Duty. So this is some sample data from a data set from a few years ago, so some of the games are a little bit old. What you can see is that they've typed in their query. The first result looks relevant, you know, Call of Duty, Black Ops, a PC game. But then the second two results, not so relevant. So they're Call of Juarez, you know, maybe there's Duty and Call and so on in the content of the page. So this is basically using Solr to index the product catalog, and this search results page is just using content only ranking. So in other words, we're just basing the list of search results here on content only. We're not making use of additional information like link and anchor text structure, and in particular for this example we're not making use of user clicks. So we're not making, for this example, not making use of previous user behavior. So that might be, that might be a search results page that appears on a lot of different e-commerce sites where they've got their standard search engine, they're indexing their product catalog, but if they haven't done the work or the system they're using doesn't make it easy to feed, clicks and previous user behavior back into the system, then they may end up getting a not so high quality set of results. So when we turn on recommendations, or we turn on the use of click signals, so exactly the same query, Call of Duty, but now we're making use of previous user behavior. So now you can see the result set is looking a lot better. So we've got 3 games, or 3 different versions of Call of Duty, and the other results have dropped out, so then they're no longer appearing. You can see, for example, the sales rank of this item here is 584. So out of the whole site, that's a pretty highly ranked item, or it's an item that a lot of people have clicked on, or people have converted, and so on. So just by having the system make use of previous user behavior, we've improved the search results, and presumably we're going to improve our conversions, which is going to improve our ROI, profits, etc., etc. So that's just a simple example of using, in this case, using Fusion and Solr. So for those who don't know, Solr, the open source search system, Lucidworks then provides a product on top of that called Fusion, which provides additional capabilities, including some of the things I'll be talking about in relation to signals and recommendations and so on. Okay, so the point about this is, I guess, why should you care? Why are signals and recommendations useful? That's a very clear, concrete, practical example of why it makes a difference. If someone turns on this feature on their website, or it's just on by default, then I claim they're going to get an increase in sales because the search results are going to be better. So here's some sample search result click events. So this is from this data set that we've been working with. This is just a simple JSON example. We've got, so each JSON record here is recording a single click event. So up here we've got a document ID, so this would refer to a product in their catalog. We've got the query that the user typed in, Call of Duty. We've got a title here of the result that they clicked on, and then we've got their user ID. So one of the key things that a system has to have access to is some kind of way of identifying not a real user, but just saying, this opaque user ID performed this action at this time. So they put in a search result, then they clicked on this result, then a few minutes later they did another search and they clicked on something else. So the point, from a privacy point of view, the system doesn't actually need to know or care about you as a real person. They just want to know that you're user 123, and by you doing these actions within a short amount of time, that's, we can make some inferences from that. So obviously privacy is a big issue in the tech industry. So that's a point that I guess I want to emphasize is that for a lot of these systems, they don't really need to know who you are as a real user. They just want to track you as what I call an opaque user ID that's moving through the system.
So would you do that only at a session level, or would you make that persistent over time?
So this user ID here is persistent over time. It's actually coming from the data set that we're working with, which was provided to us. It's not, so it's generated by some other system. But the point is, we don't need to know that this is John Smith of Santa Barbara or whatever. We just need to know that this user ID here did something at time X, and then they did something at time Y, and that's what's of interest, not who they are in actual fact. Then you can see, for example, we've got a query time or timestamp. So on the 29th of August, they submitted their query at say 8 p.m. and then they clicked on this result, a minute a minute later. So the idea is the events occurred close together in time as well. In other words, they did their query, they looked at the search results page, and then they clicked on this particular result. So this is another click event, different document ID, same query. So someone else has clicked on a different result. I mean, it's still the same. There's a lot of different versions of this game over time and different variants and so on. So someone has clicked on a different result, so it's got a different title, different user ID, and again we've recorded the query time and timestamp and so on.
Is it a Joda time? Looks like Joda time to me.
This is the default Solar ISO 8601 restricted time for us. It's basically UTC, so we're not recording a time zone. In other words, Solar at its base level wants to work with just UTC.
Right.
And then at a higher level, you're expected to, like you might want to, or you may well want to record the original time zone and convert back. Right. Which is a whole other can of worms. But from the point of view of Solar, it likes to work with UTC. Right. So these timestamps are in UTC.
Well, I guess using Joda time in Java to actually implement this, because it looks like the stringified version of Joda time.
This particular timestamp is not was not generated using Joda time, but the point here is that if you want to display the actual time that the real user performed the event, you're going to need to record that time zone because somewhere else, and then you need to convert back. Yep. Sure. Because if you just record the UTC and you don't record the time zone, then later on, if you want to present your analytics report, and people are going, well, that doesn't sound like the right time of day at all.
Right.
So we're talking. So that was an example of a click event. Here's an example of another system where we're recording events. So this is last year when I was here in the city, and I took some photos and uploaded them to Instagram. And so here I took a photo at this location and time. Then this one of the Trans-America period, and this one here. The point here to make is an event has a location and a time. Now we may not care about the physical, we may not care about the spatial location for some applications. We may not care about the time for others, and there's others where we care about both. So that's a single user. Here's an example of how having access to multiple user events gives you more information. So this is a map that someone generated from the Flickr API. So each individual dot here on this map is an individual photo that someone uploaded was geotagged with a location. So this is of San Francisco. You can see the blue dots are locals and the red is tourists. So you can see that a lot of red on the Golden Gate Bridge, a lot of red in Alcatraz, Fisherman's Wharf, and so on. So the point to make here is that all of these, if we just looked at an individual user event, it's not going to give us this information. It's only when you kind of zoom out and get that, when you get a lot of different events and you look at the larger data set, then this structure can surface. So to tie it back to the click events, if you've got just a small number of click events, it's going to be more difficult to work with. When you get a larger amount of data, you can be more confident about the inferences you're making. So just an example of some different types of event data: logs, click screens, call data records in telecommunication companies. It's a big topic in Australia at the moment, where the government wants the telecom companies to record metadata for, different phone calls, who the source was and the target, and it's been fascinating to watch politicians try to explain what metadata is, and usually not so well. Financial transactions, sensor data, you think about the sheer volume of events that are going to be recorded by sensors as well. So, this is only going to continue. There's only going to be more and more of this, data being recorded. So some characteristics of event data. It's usually denormalized, or there's a lot of redundancy. So if we went back to the example of the click records, we've got a lot of repetition there. We've got the same field. You might have different values in some cases, not the same in others. So what that means is that the raw data that you're working with is usually, there's a lot of it, and there's a lot of redundancy, and so there's opportunities then to look at aggregating and to there's opportunities to aggregate where you're not losing information, but you're just working with a smaller amount of data, which is particularly important if you want to do a lot of in-memory calculations and so on. It's often nested. So if you might have a nested, to use JSON as an example, you might have a nested schema, where you've got some top level fields and then they have child fields and so on. But it may also be schemaless, you don't, so Solar and Fusion, for example, we don't know what, particular schema or, an individual organization is going to be using with their data. And so often one of the first things that a developer or someone who's just a consultant, who's starting work on a project, they're going to need to look at some real data, some real logs, and get an understanding of what's been recorded and what's not. And often you'll find that there's a lot of information that may not be very useful for much of anything. It's just, if it's the default settings in the application that it's recording this stuff. One key point to make is that a lot of this data, if it's historical, it's immutable, so it should never change. And what that means is, from an architectural point of view, you can make some design decisions if you know that your data is immutable. So in terms of how you might design your system and your architecture and your data structures, if you know that the data that you're working with is not going to change, that can drive various decisions. And similar point, often the data is isolated, which means it can, in theory, be processed in parallel as well. So that's just some kind of high-level characteristics. Each data set that you're working with, though, is going to be slightly different. So we've been talking about individual events. To step back again, these individual events then can be defined as part of a time series. So they can be defined as a sequence of data points in time, which are typically measured at successive points in time at uniform time intervals. Again, it's going to depend on the system that's recording the data. It's going to depend on how it's been configured, what its default, how often it records or writes logs out and so on. But one of the main points to make is that it has a natural temporal ordering, so the logs that you're then working with or consuming, there should be a natural ordering to those logs. Now that doesn't mean all of the logs that are coming into your system are you might get logs from different data centers, from different systems, and they may not be in order. And so depending on how you're processing them and how your algorithm works, you may need to get them into sorted order.
The latest whammy is mobile caching.
Right.
So on your mobile device, you end up caching a dozen events and then sending it. So you've got a bunch of events coming in real time, and then a bunch of events coming in packets. And
right. Okay.
If you don't make your calls good, then that'll mess you up.
Yeah, I saw an article the other day saying that Uber relies on their drivers to store a lot of their data and then send, updates rather than trying to have some consistent central store. So I thought that was, so your point about, storing stuff up and then pushing out an update. So this is an example of a time series being graphed. So last August when I was here, there was the Napa Valley earthquake. So you can see on this seismograph, before the earthquake happens, not much seismic activity. Then the earthquake occurs, there's a big spike, and then it gradually settles down again. So the point here, we're going from we're going in time order here. This is more into the past, and then we're moving over to the right. So, you know, there's a lot of different time series out there. There's, you know, whether it's stock market data, you know, financial data, etc. There's databases that are optimized for handling time series in terms of the design decisions they've made in their architecture and so on. Here's another time series view of the same event. So this is tweets per day for the tweet earthquake. So you can see, I'm not sure what was going on back here, whether there was actually some other, you know, smaller earthquake, but you can see a similar kind of shape in that we have very little and a big uptick, you know, in the number of tweets that happened. So this, you can relate this back to, you know, the example we were looking at earlier of an e-commerce site. There may be some external news event that, you know, some new product gets launched or some new product goes viral, and then all of a sudden you've got a big spike in the number of queries or requests for that particular product, and then it may tail off again. So you were mentioning about a paper about the different shapes of these curves and so on. So that's an active area of research as well in terms of some of these, you know, you may treat as actual outliers, or, you know, maybe there's not a good reason for why they've occurred, but in many cases there is, you know, when you look at the data, there's a legitimate reason why this particular spike would occur. And then, you know, if you're recording enough data over time, you know, you'll have seasonal trends, and, you know, there'll be different queries at different times of the year and so on. So when we're talking about time series, one of the models that's used to work with time series data is a stochastic model, which, and the key point to make about this is that observations close together in time will be more closely related than observations further apart. So when we were looking at some of the sample click events earlier, we could see that someone did a query and then they clicked on a result URL, and the amount of time between those two events was pretty short, a minute or a minute and a half. So this is one of the reasons to group some event data, not all, but some, into sessions. So a session, in the way we define it, is a time window for all events generated by a given source, like a unique user ID. So again, going back to what I was talking about earlier about having that unique user ID and seeing what they're doing as they move through the system. We can then define a session to say, okay, for user 123, you know, in this short 5-minute time window, they did these actions, and so we assume that those actions are somehow related. So if someone clicks on, you know, a particular URL, and then a day later they click on another URL, well, we shouldn't be very confident that they are related. But if those two events occur quite close together in time, and that happens often enough across, you know, a set of data that we're processing, then we've much more confidence that there is some relationship between the two. So what that then allows us to do is to build up what we call a co-occurrence or adjacency matrix. So if entities frequently co-occur, we may decide that there's an interdependence between them. So for example, we could describe a click event using a click tuple with user, query, and doc ID. So again, going back to that, you know, initial example, we've got a user ID, we've got a query, and we've got a document ID, and so we can build up this tuple. And then we can then associate each of those entities with each other and with other similar events within a session. So a key point to make here in terms of the approach that we're taking here at Lucidworks is that we're generating the co-occurrence relations not just between the same field types. So we're not just looking at query pairs, for example. We're also looking at cross-field relations, so query to doc ID to user pairs, etc. And then this gives us an n by n matrix, where n is all unique instances of the field types that we're interested in. So adjacency matrices or co-occurrence matrices are used, you know, in a lot of different systems, and there's various descriptions about how they're used in, for example, the academic literature. But what we're trying to do here is not only look at cross-field relations, but we'll then look at how we're going to take that matrix that we've generated, and the next step then we use in terms of the system we've built is to then look at the graph that can be derived from that matrix and look at navigating that graph to harvest more information, which I'll explain in a little bit. So this is an example of a co-occurrence matrix. It's using the the D3.js JavaScript visualization library, and it's this is just a screenshot, but the example itself is interactive, and it's showing all the co-occurrences of key characters in the novel Les Miserables. And so you start to get these groupings of these characters, you know, frequently appear together in a chapter. The darker the color, the more, you know, the more frequently they appear together. And then we've got this user here, or sorry, not user, character, Valjean, so he's the main character in the novel, and so you can see he has a lot of interactions with a lot of other different characters. So that's just to give you an example of what a co-occurrence matrix might look like. So it's n by n. The diagonal is, you know, each individual character collocated with themselves. So we've got a diagonal line down there, and then we've got, yeah, in this case we're using, or the system is using the darkness or the strength of the color to indicate how often those characters co-occur. So the co-occurrence matrix that we can generate from event data that we're processing can be used to generate a weighted directed graph. So here, each node in the graph can be any of the types we're interested in, whether it's users, queries, sessions, documents, etc. And then the weights for the edges between the nodes in those graphs, or sorry, the graph, are the frequency of co-occurrence. So how many times the source node and the target node co-occurred. And then for a given item, so one of the reasons we're taking this approach is for a given item, we may only have a small number of items that co-occur with it. So depending on the data that you're processing and the volume and the type of data, the type of site, the type of user, you may not necessarily have a lot of co-occurrence events. You know, so if going back to the example we had earlier, where someone's typing in Call of Duty, if they end up not clicking on too many other types of document or result in their search session, and not a lot of other users do either, then in terms of a standard co-occurrence matrix approach, we don't have a lot of data to work with. So what we're doing here is by adding in the data from navigating the graph, which comes from that matrix, we increase the diversity of suggestions. And then items that appear in, so as we're navigating out across that graph from some start point, items that appear in multiple, I'm calling them lists, but you know, connections to particular nodes, items that appear multiple times are then going to rise to the top. And this helps improve the quality of the recommendations and reduce bias, and I'll show an example of what we can get from that.
So are you saying you're using both query to query and users like you also search for X, and users who did this query click this item, so you might as well?
So we're by using the cross-field occurrences, so we look for cross-fields, when I say fields, so different types, so user, query, document, etc. By mining the cross-field linkages, we get more information to build up our adjacency matrix, and then that then allows us to navigate out from a particular item that we're interested in and harvest, as you say, then users who clicked on this. But the point is we don't care a priori about what's linked to from the node. We're not saying, okay, we're only interested in what other users did. We're navigating out and then we're harvesting it, entities that are of interest, and I'll give an example. So this is an example of an aggregated record. So this is the same data set that we looked at earlier. So earlier we were showing sample individual click events. What we're showing here is then an aggregated record that Fusion has generated. So you can think of this as a synthetic document. We've taken the raw input data, the raw logs, and we're then generating this aggregated record, and we're going to index that with Solr, and then that's going to allow us to do some of the graph navigation and other stuff. So for example, for this original query, Call of Duty, which was the example we're working with, we've got a list of outgoing clicks. So these are document IDs that users clicked on. We've got counts. So this document here was clicked 309 times in connection with that query. So this is the number one clicked document for that query. Now we drop down to 187, so you can see that we're starting to drop off pretty quickly. So the second document here was clicked on 187, and so on. You can see how it drops down pretty rapidly. We've got session IDs that have been, we've derived, this process of sessionization to say, okay, here's a unique user, they've done this particular action at time X, and now we're going to start a timer, and we're going to, so say for 5 minutes, if they do any other actions in the next 5 minutes, then that's considered part of that session. And that then is what allows us to say, if from that session data to say, well, because that session data is time bounded, we have a reasonable confidence that events that co-occurred within those sessions, there is some relationship. So yeah, we've got incoming session IDs, we've got incoming user IDs. So when I say incoming, they're, this session resulted in this query, or this user manually typed in this query. So we're using in and out here in the graph sense. So we're saying for this particular node here, this Call of Duty query that we consider a node in our graph, we've got ingoing and outgoing edges or links. We've got some co-occurring queries. So these are other queries that co-occurred in the sessions that we've mined. So these are the names of other console games that are in the same genre: Battlefield 3, Gears of War, Call of Duty, etc. And then we've also got counts for those individual. So a lot of these individual fields that have text items, we've got a parallel counts field as well that's recording the counts. So this is something that Solr can work very well with. It doesn't require some special schema. This is pretty flat structure, and it allows us to work pretty easily with this data in Solr in terms of us constructing automated queries and so on to work with the data. So at the end, what we get out, if we say for this query, show me some recommendations, we get a list of related document IDs, and we get weights associated with those, and we get a list of related queries. So this information then is coming from navigating out from the graph, and I'm going to show an example of that in a second. The point being here is, for example, a lot of these related document IDs are not documents that were clicked on in relation to Call of Duty. So when we talk about mining some of that historical data and saying, well, other users who typed in this query clicked on these other documents, this set of suggestions is not biased towards that, because we're navigating out using the graph, and we're mining other related information. And similarly for the related queries. So I keep talking about graph navigation, so I'm going to go through a worked example. So here we've got a query Batman, which is another game in this data set, another video game. So this is a query. So this is a node in the graph, and we're at a distance of 0 from this node. So this is the node on its own with no other, we haven't navigated out at all, we're at our starting point. Then we navigate out to a distance of 1. So these are session nodes. So a point to make here, we're treating sessions, users, documents, and queries as nodes. They're all on a conceptual level, they're all on the same level. So we're saying there's a distance of 1 between this session. So this session resulted in this query being run, and then it resulted in this document being clicked on. The size of the nodes here is showing that this Batman Arkham City received a lot of clicks, and we'll see as we move further out in the graph, we'll see why that is. So the point here is these are all all of these nodes are reachable as a distance of 1 from the start point. So now we go out to a distance of 2. So now we're picking up some additional queries. So the nodes in blue are queries. So we've got this document here that's receiving a lot of clicks from different queries and different users. Here's our original query still highlighted. And here's some various Batman Arkham City, Arkham City Collector's Edition, and so on. So the blue nodes being queries, the yellow nodes sessions, and then the green nodes are individual user IDs. So the users have initiated a session, they've run a query, and then they've clicked on a result. So this is, apart from anything else, this seems to me is a useful way of visualizing user behavior in terms of an individual. So for example, if an e-commerce site is interested in their top products and they want to understand how users are interacting with them, then this is a way of visualizing the user behavior I guess, similar in some sense to Google Analytics kind of flow and funnel diagrams and so on.
I got a fun one for you. This is my data on similarly. The connection between Disney and Breaking Bad. how are Disney, how they're
Million dollar.
Okay, so we're at distance 2 now. So we started off distance 0. You know, we were at the starting point. Distance 1, we got some sessions and a query, and then distance 2, you can see how the graph is, you know, expanding pretty rapidly. Distance 3, so we've picked up some more users. I think we might have picked up another document as well. So you can see that this document here, the collector's edition, is not receiving as many clicks as the main type, presumably because it's more expensive. Which goes back to the point about if an e-commerce site wants to analyze, you know, how users are behaving with their particular products and product variants, this could be a useful way of visualizing it. And then we go out, in this case, I'm saying unlimited, so I've told the program to generate the graph, you know, from the start point to no limit, and this is all of the nodes that are surrounding that original start point, which is still highlighted here. So this example here, we can then say we want to navigate out from the start point. So if someone says, give me some recommendations for an individual item, whether it's a user, a query, a document, we can navigate out pretty quickly because we're not navigating the entire graph. That's the key point to make. We're just navigating the neighborhood of the individual entity that we've been asked about. So if you want to navigate, you know, the full graph, all of the different connections, all of the different nodes, that's going to be, for any reasonable data set size, is going to be expensive. But for navigating the neighborhood of an individual item, it's tractable, and it can be done. It can actually be done at basically recommend or request time. So we're not pre-computing the graph navigation. We're pre-computing the adjacency matrix. We're pre-computing some other stuff, but the actual graph navigation, in this case, can and is done at request time. So a reminder: this was the example where the user typed Call of Duty, and we were including click data, so we had our better set of results in terms of these are all, you know, more relevant products for that query compared to if we're not using click signals at all. If we then made recommendations from just the top clicks for that query, they're still useful. You know, they're a set of Call of Duty recommendations, but actually, if you see, they're not surprisingly, they're pretty similar to this list because this list is based on the top clicks information anyway. In other words, we're boosting these documents or results because they received a lot of clicks. So unsurprisingly, if we just did a simple recommender saying, you know, for this query, what were the top clicks and recommend them, we're not giving the user much, you know, new additional information. If we use the additional graph navigation data, now we're picking up Battlefield 3, Batman. So these are all products that were picked up by navigating the graph. From looking at the data and looking at the graph, you know, and seeing what the user behavior was. You know, Battlefield 3 is basically a similar game to Call of Duty. From an e-commerce point of view, this is about diversity. It's about suggesting other products that are similar to the one that the user was searching for, but it's not, we're able to expand the set of possible items that we can recommend to them. And the last point to make is that using signals is about modifying your behavior in response to your environment. So if you think about, you know, if you build a particular service, whether it's a website or some internal system or whatever, and then you record user data, if you're not making use of that data, then your system is not actually responding to its environment. Whether there might be internal events, you know, there might be internal program states that you're interested in, or there might be external, you know, end users clicking on particular things, not clicking on other things, and so on. If you're not making use of that, then, you know, your system is not learning and it's not evolving and it's not responding to the environment. And I claim that by starting to using signals in your system, that you're gonna get a better user experience, because new users coming in can benefit from previous user behavior. So you might have a user that comes into your site that has no history with your site, that never used it before. So it's what they call a cold start problem for that user. You don't have any previous history. but a lot of the recommendations that we could make to that user can be based on previous user behavior that is independent of what they might do and so on. So yeah, the key point to make is that the more you can feed that signal information back into your system, you're closing that loop, and you're, I mean, you can't just do it blindly though. You have to, if you had a system that decided that, well, if we lower prices slightly, sales go up, so let's keep lowering prices, and we get down to $0, sales have boomed and profits have tanked, you need to understand what you're doing, but the point is that if you're not taking note of that signal data at all, then your system is in some sense static, and it's not going to be as responsive to end users, and then that's going to have an impact on how successful your service or your business is. Okay, so any questions?
So,
Yep.
so basically, so you're using doc values, right, for like a graph construction. So
Sorry, what do you mean doc values? What?
doc values.